Hi. What I'd like to do is to give you a brief tutorial here on how to integrate products of trig functions that are in this form or that are in this form. There's a couple of reasons for that. These forms show up often as the result of some kind of trigonometric substitution, which we'll cover at a later time. And so what we would like to be able to do is to integrate these as conveniently as possible. And we're going to take each one in turn. The big theme here is to find a du. That's really the big idea. So as we walk through various examples of these integrals, what we're going to be doing is looking for a du. So I'd like to start with the integrals of products of sine and cosine. And the big idea here is that if I choose a u that is sine x, then immediately du is cosine x dx. Or if I choose u is equal to cosine x, then du is negative sine x dx. And just a little bit of repair gets me there. So, keeping with this idea of find your du, let's take a look at some integrals that are in this form. First of all, let's consider the integral of sine squared x times cosine x dx. This one's pretty straightforward. When I take a look at this, I can see that I have a cosine x dx that's sitting right there. So it's pretty obvious that I want to let u equal sine x. And therefore, I have du as cosine x dx. And what I really have then is the integral of u squared du. And I can integrate this form immediately, and we're done. See, it's very straightforward. The key was looking for the du. As these integrals get more complicated, the same principle applies. But we may have to be a little bit more creative about it. What are my options here? Well, I could choose a u equals sine x and a du is equal to cosine x dx. Or I could choose a u equals cosine x and a du is negative sine x dx. Which one is the better choice? Well, the better choice is actually the u equals cosine x. And the reason for that is that I have an odd power of sine here. And because I have an odd power of sine, what I can do is to peel off that odd power of sine as a first step to isolate my du. Here it is. So there's my du, except for the negative 1, of course. And then as a second step, I can take even powers of sine and rewrite them using the Pythagorean identity. Because sine squared is 1 minus cosine squared, I now have this integral right here. Now how does this work out? Well, let's distribute and see what happens. This gives us the integral of cosine squared x sine x dx minus the integral of cosine to the fourth x sine x dx. And now, as if by mathemagic, I have arrived at two integrals that are very, very easy. I have u squared times negative du, which gives me negative 1/3 cosine cubed x, minus, this is u to the fourth, negative du again, so it's really plus 1/5 cosine to the fifth x plus c, and we're done. So in the case where I have an odd power of sine or cosine, I can peel off that odd factor as a du, and then use the Pythagorean identity to convert the rest of the factors into one trig function only. What I'm aiming for is an integral that is in the form u to some power times du. The only place where this gets tricky is if I don't have an odd power of sine or cosine. If both powers are even, then I have to resort to double angle identities. So let me remind you of those. The double angle identities look like this. Cosine squared x is the same as 1 plus cosine of 2x divided by 2. And sine squared x is equal to 1 minus the cosine of 2x divided by 2. So that if I have something like the integral of cosine squared x, sine squared x dx, then because both of my powers of sine and cosine are even, I am not going to be successful at peeling off a factor of sine x to be a du, or a factor of cosine x to be a du. You're welcome to try that, by the way, and you'll see exactly why that is so. Instead, I'm going to resort to the double angle identity. I'm going to replace cosine squared x with what it is, and sine squared x with what it is, and now I have a factor of 1/4 that can come to the outside, and when I multiply here, I get 1 minus cosine squared of 2x, like so, and 1 minus cosine squared 2x is the same as sine squared 2x. And now, once again, I have a situation where I have even powers of sine and cosine. The power of cosine is 0, of course. So I'm going to use the double angle identity one more time. Sine squared of 2x is 1 minus cosine of 4x divided by 2. So that when the dust settles, I have finally worked my way down to the point where I have an integrand that can be done by repair like so. These are much more of a pain in the neck than the odd powers of sine and cosine. So just to rehearse what we've said so far, if I have an odd power of either sine or cosine, I'm golden. Or if I have an odd power of both, I'm good. Then I'm going to reserve sine x dx or cosine x dx as du, and then I will convert using Pythagorean identity. If I happen to have even powers of both, and I groan and I pull on my double angle boots and convert. And that's it for integrating powers of sine and cosine. The best way to get used to these, by the way, is to set problems for yourself, practice with them, and then take the derivatives to see that they check out. All right, let's consider integrals of secants and tangents. Again, our theme is find the du. And since the derivative of tangent x is secant squared x, and since the derivative of secant x is secant x tangent x, what I'm going to be doing is looking to isolate either a secant squared or a secant tangent as my du. That's the basic game plan. So let's consider this integral, the integral of secant squared x over tangent x. All right, so I look here and I see that, aha, I have a secant squared x dx, and that can immediately be du. if u is tangent x. So that my integral is now in the form du over u, and immediately I get the natural log of the absolute value of tangent x plus c. Very, very straightforward. Likewise, if I have something that looks more sophisticated, like the integral of secant to the fourth x dx, then I can reserve for myself a du, find that du, and I have secant squared x left over. Because secant squared x is the derivative of tangent x, I know that I want to convert all of these factors here into tangents. And I'm going to use that with, you guessed it, Pythagorean identity. Secant squared x is tangent squared x plus 1. And so now when I distribute, I get two easy integrations, u squared du and just plain old du. So that I get 1/3 tangent cubed x plus tangent x plus the obligatory constant c. This kind of thing can work just as well if I have the integral of tangent cubed x. At first it looks like I'm toast because I don't have a factor of secant squared, but then I remember to myself, oh yeah, that's right, Pythagorean identity, secant squared is tangent squared plus 1, so tangent squared is secant squared minus 1. And so this gives me the integral of tangent x secant squared x minus the integral of tangent x dx. Now, this integral right here is just u to u, so I get 1/2 tangent squared. And the integral of tangent x, you remember, we handled by thinking of it as sine over cosine, so that we have du over u, and we get the natural log of secant plus c. So much for that. Sometimes, however, we end up in situations where we don't have even powers of secant. And if we don't have even powers of secant, it can be very awkward to peel off secant squared. So in those circumstances, I look for another possibility. And that possibility is that maybe I can peel off a secant tangent. And that's exactly what we have here. Here, I find my du as secant x tangent x, leaving me with u squared du. And that's immediately 1/3 u cubed plus c. So this is also very, very straightforward. Something more complicated. Well, yeah, that'll do. The only problem that I run into is if I have even powers of tangent, but odd powers of secant. For example, the integral of secant cubed x dx. And the reason that this particular configuration is hard to work with is that because I have even powers of tangent, it will not be productive to peel off a secant tangent. And because I have odd powers of secant, it will not be productive to peel off secant squared. So I'm kind of stuck. This is sort of like the case we had where we had even powers of both sine and cosine before. And the way that I'm going to handle it, this is a good example of this. I have an odd power of secant, and I have tangent to the 0, which is an even number. The way I'm going to handle it is with parts. I'm going to integrate by parts, letting u equal secant x and dv be secant squared x dx. We actually did this integral before when we did parts, but it's worth doing a second time. So if I identify that as u and dv, then I get du is equal to secant x tangent x dx, and v is equal to tangent. So that this integral is equal to u times v, or secant x times tangent x. Oh, we don't need a dx right there, thank you. Less the integral of v du, or tangent x times secant x tangent x dx. Let's clean this up a little bit and see where we stand. At first it looks like we have made things worse, but then I realized that tangent squared is secant squared minus 1. And when I distribute, then something lovely happens. I get the integral of secant cubed x dx plus the integral of secant x dx. And keep in mind that this whole thing, to begin with, was the integral of secant cubed x dx, so that I can add one integral of secant cubed x dx to both sides. And I remember that the integral of secant is natural log of secant plus tangent. And so we just need a little bit of division to carry us home. And there it is. This is the most complicated case, where we have odd powers of secant and even powers of tangent, and when we have that situation, the indicated method is parts. So let's review. Our big idea, well, where are we? There. Our big idea is to find the du, and the du's that we're looking for are going to be sine x dx or cosine x dx if we can find them. If we cannot, if we have even powers of both, then we're going to resort to double angle identities for sine and cosine. For the secants and tangents, we're going to try to find a du in the form of secant squared or secant x tangent x. If we can do that, great. If we cannot, because the power of secant is odd, the power of tangent is even,